Hello everyone, my name is Alessandra Hausmann and I would like to take you on a short journey into the world of powder caking and how we change the FT4 from Freeman technology in a way that we can humidity control airflow and with that actually monitor caking in situ. All right, so why would you even care about this topic, right? Solids handling is important across industries, so wherever powdered product is present, not only, but especially in the pharmaceuticals industry. And it has grown in importance as supply chains get more and more globalized. Down here you can see 3 images of so-called big bags. That's where powder is usually conveyed and transported in. So when a free-flowing powder like this ends up like that, we speak of powder caking. So there are many types of wanted agglomeration processes within particle technology. This is unwanted agglomeration. What is actually quite interesting is that the products you can see here in these 5-liter buckets are chemically speaking the same, and still their degree in caking varies largely. So what factors actually play a role in caking? There are constituents such as impurities, additives, coatings, feedstock source. Then there are processing variabilities. So the type of packaging is actually quite important, and the way it's transported or stored. And also processing steps. And then there are intrinsic material properties, which is my focus. So going from inside out, that would be starting at the molecular structure of the particle, going to its supramolecular order, leading to particle properties such as particle size distribution, particle morphology, surface energy. All of these things. As if that wasn't complex enough, many of these factors are influenced by pressure gradients within the bags, a change in temperature, time, or humidity. Humidity is actually key. Why? Because humidity can lead to phase changes within the material. Actually, humidity is everywhere. So water molecules are absorbed on every surface that you can see if you just look around now in front of your laptop or desktop. If we would really want to get rid of all moisture within a particle, we would have to vacuum dry it. If we then increase in relative humidity from just the adsorbed surface, it will lead to multi-layer adsorption and then to capillary condensation and eventually to deliquescence. Deliquescence is a process in which the surface of the particle gets solubilized. If we would then dry the particles, there could be solid bridge formation, hence caking. In amorphous powders, still humidity is an important factor, but in a little bit of a different way, because water doesn't only get adsorbed, but also absorbed, meaning it goes into the bulk of the powder, of the particle, where it can act as plasticizer, leading to a decrease in the glass transition temperature of the material. And so you have kind of a viscosity-driven caking. Actually, caking as a problem is as old as particles themselves, I'd say. So how is this problem tackled in industry nowadays? How it is still characterized largely? Of course, there are many new methods out there, but still often industry relies on either humidity-controlled shear tests or humidity-controlled caking studies. These caking studies are just bags. They are filled with powder, and then they are put into an environmental chamber. Then they just wait and for up to 3 months. And basically then the caking strength is mechanically tested. We believe that we can do that a bit faster and hopefully also in a way that we will afterwards get more insight into the caking mechanism, which would then lead to just an easier way to find a solution for the problem. Our approach is to humidity-controlled powder flow. On the next slide, you can see a little bit, like just a summary of a lot of ways, characterization techniques to characterize powder flow, and also to how that is like in a compressed state. However, we want to take a closer look actually at the FT4, which is a really nice piece of equipment because it comes with so much freedom for you to develop your own methods with the equipment it comes with. So you have the blade, the vented piston that you can compress the powder bed, a shear cell, different vessel sizes, all of these things to basically make your own method. Maybe let's first take a look at the way it measures powder flowability. So in a standard measurement, first there are conditioning cycles where just sort of the history of the powder is supposed to get erased by mechanical conditioning, where the blade goes into the powder bed and up again. Afterwards, the vessel is split. This is how we confine the volume and also the density of the powder bed, and then then the normal test is performed with conditioning and test cycles. How they derive at the flowability energy is this blade basically measures the instrument measures the force the blade takes to go down through the powder bed, that's this part, and to torque within the powder bed, and that's this part. And then it adds it up basically over the whole movement of the going downward and upwards again. Let's take a look at a standard flowability measurement. So usually there would be 11 cycles, and the tip speed would decrease within the last cycles. And at the 7th test cycle, the basic flowability energy is taken from. Here you can see a measurement with some of the materials we have that are chemically, again, the same, but are very different in the particle shape. And you can see that especially M3 and M5 here, there is a decrease within the first 3 to 4 cycles, a large decrease in the energy the blade requires to go through the powder bed. And we believe that that is probably due to them being so long needles. And because in the 25 millimeters vessel, the distance between the blade and the vessel is just 750 micron, you can easily imagine that there might be a problem with these needle-shaped particles. But maybe it's more interesting now to see what we actually did. So the air control unit is just normally connected to an air supply and would then actually be directly connected to the FT4. But in our case, it is connected to first the air drying unit, then the air humidifier unit, where we can program directly what relative humidity we want to introduce then into the vessel. How is the humidity introduced? You can see here the aeration base. There is a grid here where then the air can get introduced into the vessel. Yeah, and this is our humidity controlled FT4. With the tests, we changed the protocol so that we can actually perform 80 test cycles. The first 20 cycles are without the aeration mode, so no relative humidity is introduced. Between cycle 20 and cycle 60, the aeration mode is turned on and there is relative humidity. Still, we are here below the deliquescence point. And then afterwards, again, you can see that it roughly returns. the aeration mode is turned off again. There are different features I want to highlight in this graph. First of all, these are replicates, and the standard deviation decreases as soon as we turn on the humidity control. Second of all, we can see that the material within the first 10 cycles is actually quite unstable. So maybe the standard protocol would not be suitable for this type of material. And third of all, like obviously, there is like a decline in total energy upon us turning on the aeration control unit and it turning on the aeration mode. There might be several reasons for this. Of course, we did consider the powder bed just getting fluidized, but in this case, that's not the case because we did backup measurements and different relative humidities to prove that that is not the case. Our current hypothesis, and we are trying to quantify this, is that this is due to electrostatics. I mean, we all know that there is triboelectrification and powders might get charged, and that is, and humidity can dissipate some of that charge. And we also believe that charge could be one of the reasons for the decline within the first 10 cycles here, because the blade is going through the powder bed, and then there are two possible effects in terms of electrostatics. One of them is maybe charge gets dissipated through the blade, and the other is maybe charge gets actually introduced into the system through the blade. All right, so far we have only looked at measurements below the deliquescence point for crystalline materials with a particle size of roughly 500 micron. Let's now look at the same crystalline material, but with a particle size of 300 micron, and where we can actually see caking. So here you can see three measurements. One of them is without any aeration mode on. So just to see if the material is even stable, mechanically stable for this time. The second one is below the deliquescence point, so the red one that goes down here. And the third one is measuring above the deliquescence point of the material. Again, within the first 20 cycles, that part really depends on also the history of the powder. I just want to show that there is quite some deviation, and this is very the measurement protocol is very important, especially for problem powders, as you might want to sieve them or you might want to mix them, and all of this might also induce charge. And then, but the actually interesting part is that when we are above the relative humidity of deliquescence, when we expect the surface of the particle to get solubilized and caking to start, we can see that the total energy the blade needs to go through the powder bed increases. So we can actually see in-situ caking. For these two measurements, we took images of the powder after the test and of the vessel. So for the blue measurement, you can see that some of the product actually even caked within the vessel down here. And also just the way the powder looks like is very different from if we measured it below the deliquescence point. I want to stress out that this experiment takes about 2 hours, which is orders of magnitude different from 3 months. To conclude and give an outlook, I think I kind of teased a little bit our results and what might there be to come still, hopefully within the next months. We showed that we have a promising technique to look at not only caking, but also electrostatics of powders with the FT4. Then, of course, what we are planning to do is to do that not only for crystalline materials, but also for amorphous materials, look at different classes, look at maybe also different measurement protocols with the FT4, and then to correlate our findings with the FT4 to findings we get with the DBS and indentation. So indentation we do, these we do for just the caking studies to see if we can replicate what they find out with 3 months, basically. And the DVS, we do experiments with to look at the sorption dynamics of the sample, to see if maybe also with the DVS we can find hints to powder caking. I actually have some interesting backup slides, but unfortunately, like for indentation and DVS, but unfortunately this format doesn't really allow me to show you. But if you have any questions or in general interest in powder caking, please reach out. I also really deeply believe in collaborations within research, and that kind of brings things forward. Last but not least, I would like to also thank BASF for their kind financial support in this project. In general, Freeman Technology and all their people for their support with the methods and many of my questions. Roquette for providing some of the materials, and you for your attention. Yeah, bye.